Okay, so we discussed three different differential amplifier topologies yesterday, and we are going to build on the top of that and try to look at op-amp schemes based on these differential amplifier. Um, so in these differential amplifiers also we can design them to have high gain. For example, currently he was not able to improve the gain further than say around 55 dB, 56 dB, which is also a good gain for this topology. Um, but let us see, how to make a two-stage op-amp using some of the schemes that we discussed and how to arrive at the gain of those schemes. So a relatively common op-amp structure that we see, two-stage op-amp. What is happening? So let me increase the size a bit. So two-stage op-amp. So this one is uh, used popularly, but again, at scaled nodes, people avoid this one because of some reasons. Let us see what is the scheme. So we have already, I think, discussed this amplifier. You have simulated it today. So let us start with this particular topology. All of you are able to see hear me clearly. I hope the volume is not too low. Volume is coming properly.
Yes. Yes, sir.
So here we have this M1, M2, M3, M4, M5. And I hope all of you are able to see it in the full screen, right? Because if you don't see it in full screen, then the font, etc., may not appear very visible. So you should open the full screen mode while viewing the live session. Are you doing that, everybody?
Yes.
Okay, so here we have V plus, V minus, and in fact, we will have to reverse this polarity. Let us do this later. All we do is after the first stage, this we can call it V out one, we put another common source. So in order to have a higher gain, you need to add a gain stage. So a popular gain stage is just a common source amplifier. But the question here is, what kind of common source amplifier should I put? So whether if it is an active load common source amplifier, then what kind of input device? PMOS input device or NMOS input device? There are two options, right? So I can have a common source amplifier with NMOS input device, and I can have a common source amplifier with PMOS input device. What should I put? Yes.
CMOS.
Okay. PMOS, why?
So because if we use NMOS, then it may hinder the swing.
If you use NMOS, then
The swing will reduce.
why the swing will reduce? What happens if I, put an NMOS? And the load can be anything. Load can be active load, PMOS. What is the problem? What is the problem? Yes, anybody? What is the problem?
Sir, my output swing of the second stage may reduce because I know that of the second stage, my minimum value of VD should be VG minus of VTH, and VG is the V out of the first stage, which is already, sir, being amplified by the first stage. So it will already uh, in the high when V out is high values, this thing may reduce the lowermost point of voltage swing, and thus the total output voltage swing will decrease.
So the V out is at the highest value. So going all the way to say VDD, close to VDD. At that point, what is the problem?
That the problem is
Here
that
output will
yes, sir, the output will be lower because I know because for this to remain in saturation, it should be this output voltage should be greater than this VG minus VTH, and VG is at the highest point, so it may fall out.
swing is not really the consideration for the first stage. First stage is anyway, in this case, because if you're applying two-stage amplifier, if it is operated in open loop case, so the larger swing will come at the output, the second output. The first output will have lesser swing. The way we will design it is such that, the maximum swing or the output swing full value should be within 0 to VDD. And therefore, the swing at the second stage will be more, swing at the first stage will be lesser. Because eventually, while designing any amplifier, we have to make sure that whatever is the output swing, that is within 0 to VDD. So in case of swing, like why it is affecting the swing? Because of the DC level, right? So the DC, if you look at the V out 1, what is the DC level of V out 1? It is divided by, again, I bias and the W by L of these M3, M4, because this gate of M3, M4, VG4 is VDD minus VSG of M3, M4. And that depends on W by L of M3, M4. So this is VDD minus VSG. So if you just put some numbers, VDD suppose 1 volt and VDD minus VSG, that means ultimately you're talking about what is the VSG of this MOSFET. VSG will be somewhere close to VT. So what is VSG for any NMOS? We call it VGS will be equal to VT plus V over drive. Remember, right? The V over drive is defined as VGS minus VT. Likewise, for PMOS VSG, we can define it as mod VT plus V over drive, because again, V over drive is just VSG minus mod VT. So what is how large is the VSG as compared to VT is the overdrive voltage. So now in this case, this is something like the VSG of PMOS. So if I just write it, VT may be around 0.3 volt, V overdrive maybe 0.1 volt. So it's around 0.4 volt. So 1 volt minus 0.4 volt, something like that. So it is something like 0.6 volt. So this 0.6 volt, if it comes here 0.6 volt, this will be, giving you a large VT. So the VGS of the NMOS, VGS of NMOS will be in this case 0.2 volt. So first of all, it will take more current, right? So the DC current in this case will be controlled by the DC current of this level. So now the DC level here itself is 0.6 volt. And first of all, in this case, the overdrive voltage is now 0.2 volt rather than, there is no direct relation between the overdrive voltage of this stage, the NMOS over here, and the overdrive voltage of the NMOS in the other stage, like M5 over here. So here, definitely, first of all, it is leading to a higher overdrive voltage. And second thing is, now if you put the same overdrive voltage here, like how do you bias the VB? VB, in this case, if we try to derive it from some other source, again, it will complicate the design. We can't definitely take it from the same value here. So we can't use this point any longer to bias VB, because now M4 is, if we do that, then this will also become 0.6 volt. And then you have again a large VSG for the PMOS also. So if you have a large VGS for NMOS as compared to 0.1 volt, now you're having 0.2 volt. That means the DC bias current here will be more. And second thing is the output side. If you look at the lower potential, minimum that you can get is VGS minus VT. So VGS minus VT is your V out mean. Now, since the gate voltage is higher, the lower side, the swing will be getting affected. So it will be lower than expected. So both the things are there. It is increasing the overdrive voltage, and therefore the IB 2 you call it, the bias current in the second stage will be increased because we are using a larger VGS for the NMOS. We are forcing the gate voltage of this NMOS to be dictated by the gate voltage of PMOS, which is higher. And as a result, the IB2 will be bigger because remember there is a square dependency. So rather than keeping a 0.1 volt of overdrive voltage, if you keep 0.2, that will lead to much larger increase in the bias current. So IB2 will be significantly bigger than IB. We don't have much control how to, make sure that IB2 is comparable or equal to IB. So in this case, it is, there is less control on the bias current of the second stage, and that leads to more power consumption. And second thing is the output swing also getting affected. Gain also gets affected because if the bias current is more in the output stage, automatically it will lead to lesser gain. So gain will drop, bias current will be more, power consumption will be more. And second thing is your output swing is also lesser. Is that clear? Therefore, we will not go for this. So what we go for is a PMOS input device, because now, is this clear? Whatever I spoke is clear to everyone?
Yes, sir.
So here we are having power of second stage high, bias current, and power of second stage high. Then output, you have your output swing at second stage. Output means final output only, so I don't need to write second stage. That will be lower. And we also have biasing difficulty. VB has to be biased. And there is no correlation between the bias current IB2 and IB. So it has to be, we are not able to control it specifically. We are not able to maintain a desired IB2. And the gain point of view also, you are going to get lower because of larger bias current. So now, rather than doing that, we will go for a PMOS input stage. So now you have the VSG, whatever you had, whatever V overdrive voltage you are having for the PMOS here, you will have the same for the output state. So if I again call it 1, 2, 3, 4, 5, 6, 7. So the VSG of 6 is equal to VSG of 3 and 4. Therefore, if the W by L ratios are same, that means W by L of M5, sorry, W by L of M6 is same as 3 and 4, you will get the same current. The bias current in this one will be IB by 2. So if this is IB, you are getting IB by 2 here. As a result, if the Ws are same, you will get same IB by 2 here. So the bias current is well controlled. It is defined by the bias current in the first stage itself. What about this particular thing? How will you size this M7? M7, what should be the size? How will you decide? Yes, anybody?
So it should have a higher length because the gain provided by the second stage will basically GMP RP parallel RN, right? So since the GM of the NMOS is not concerned, so we can keep the length high while keeping the W by L ratio low. And then we can bias it using the current source, current mirror, which is biasing my IB, and such that it comes as half here. Like the W by L ratio of 5 should be double of that of 7. Yes.
Yes, because here, if we have IB by 2, we need to make sure that M7 is also biased such that it also supports IB by 2. So in order to get IB by 2 in M7, we already have IB in M5. So if I make the W by L of M7, W by L of 7 equal to half of W by L of 5, then we automatically we are biasing M7 also for IB by 2. So depending upon what is the ratio between M6 and M4, we need to decide the ratio of M5 and N7, right? So this is clear to all of you? So in this case, what is the overall small signal gain? What is the small signal gain?
Sir, GMR means GM1 into R are out of 3 and 4. That is either of R of 3 or 4 multiplied by GM6 R6 parallel R7.
Yes, so gain overall will be A1 into A2. A1 gain we have studied yesterday, which is going to be equal to GM1. Here, RO4 parallel RO2, right? So RO4 parallel RO2 minus sign multiplied by the second stage gain, which is A2, which is GM6 minus GM6 into RO6 parallel RO7. Minus gets, plus. So if you are considering this, now in this case, what is going to be the positive terminal? What is going to be the negative terminal? If I consider this as the output, from which is a positive terminal? Input side, which one is going to be positive? This will be positive, right? Because if you increase this will reduce, this will increase. So whatever terminal leads to increase in output voltage while increasing the input voltage will be positive terminal. So in this case, if this M2 gate is increased, first stage you will get reduction, and then that will lead to increase in the second stage. So this is positive terminal, and this is a negative terminal. So in your op-amp, the way you design, this symbol that you design, minus, plus. So in this case, the negative terminal will be gate of M1, positive terminal will be gate of M2. Is that clear? Any doubt in this? So gain, we can see that definitely now, whatever you were getting from single stage GMRO, because the order of gain was GMRO earlier. But now the order of gain is GMRO whole square, because first stage GMRO is coming, second stage again GMRO is coming. So this scheme can give you bigger gain. So if you're getting a gain of 100, from the previous scheme, suppose you are getting 500. Now in this case, you can get 500 times 500. So this can give you overall larger gain. What about the all other analysis like the input common mode range, etc., that you can see? Now, what about the bandwidth? So here, what are the critical poles? What are the critical poles? Which node will provide you critical poles? Yes, anybody? In this circuit, which nodes will provide you the critical poles?
So my final output node, that will be a critical node, because in that I have a resistance of ROP parallel RON, that is RO7 parallel RO6, and the this first stage output, that will also give me another pole, significant pole.
Yes. So in this case, in this amplifier, the pole, high frequency pole, if I see here, this node is a low impedance node, because here the net impedance, if I call it, say, whatever, node A, node B, node C, node D. So for differential operation, node D is not consequential. We assume it is AC ground, right? So node D is not important. Only for common mode gain, it will be important. For common mode gain, high frequency, you remember what happens? Common mode gain starts increasing at higher frequency. Why it increases? For common mode gain, why it increases at higher frequency? Yes, anybody? What is the common mode half circuit? Common mode half circuit. Common mode half circuit. Is this clear? This is common mode half circuit.
Yes, sir.
So because when you look at common mode, the two inputs are tied up, and A and B are going to be together. So we can assume that A and B are following each other. We can just tie A and B also, and therefore this is the common mode half circuit. So for common mode half circuit, overall gain in this case will be dependent upon what? Like ultimately it is a common source amplifier with a source degeneration resistance. So why does the common mode gain degrades? That means it increases at high frequency. Common mode performance degrades means common mode gain is increasing. So at higher frequency, what I say is the common mode gain will increase. Why will it increase? You have studied the frequency response of differential amplifier. Yes, hello. How will you decide the frequency response of this common mode amplifier?
Sir, one reason may be that the parasitic capacitance.
Parasitic capacitance is where?
Hello.
Which node parasitic capacitance will affect the common mode gain?
Hello.
Yes, am I audible?
Drain to source, sir.
Of what?
Of fifth one, sir. M5.
So you have several caps, right? So at this node, if I look at the cap, you will get this cap. You will get, this body terminal is grounded. You will get this cap. This body terminal is going to be grounded. You will get this cap, right? You will get the Miller breakdown of this CGS also. You will get something, like this. Effectively, you will get some cap here, right? Effectively, because of all these parasitics. Is that clear? So this
Yes, sir.
overall capacitor at this node will lead to, at higher frequency, what will it do? If I assume that, there is I replace this with an equivalent cap CS. At higher frequency, you are having a small signal impedance given by this M5. So you have an RO5, and CS. So at higher frequency, what will happen? This RO5 and CS, the CS will try to short the RO5. That means it will try to bypass the RO5. As a result, it will start behaving like a common source amplifier without source generation. Is that clear? Because of the parasitic effects, the source degeneration effect of the M5 starts degrading. As a result, common mode gain will increase at higher frequency. But then also the upper side, you have additional poles over here because of the capacitor. So this poles will again further try to bring it down. So it will increase, but then finally the two effects will try to cancel out each other. So to some extent, it will balance out. But as compared to the DC value, it will increase initially and then stabilize to some value. So therefore, common mode gain will be something like, initially it will be low, and then it will start increasing at the pole given by this particular node. And then when this pole comes, the pole of the upper node, then it may again start. So again, in order to generally, because here we are keeping the M5 dimensions will be bigger, is the current source device. So W will be bigger, L may be also bigger. M1 also generally we keep the W and N bigger, right? So gain has to be big. So therefore the M5 device, so M1, M2 device, input devices, even W by L will be bigger. So as a result, the net capacitance here may be significant. And these two nodes may be comparable because here also we are having small impedance 1 upon GM. On this side also we are having, equivalent impedance is still less, but the capacitance can be more. As a result, you can get significant, increase in the common mode gain at lower frequency. Sorry, higher frequency. But then when the pole of this node comes, it is trying to, bring it down again. So there is a zero effect coming. So there is a zero and there is a pole. So the zero effect will try to increase the common mode gain, trying to bypass the source degeneration resistor provided by M5. The equivalent source degeneration effect is getting cancelled. Is that clear? So if you have studied the frequency response of the source degeneration resistor, that also looks like this only, right? So You might have studied two cases with bypassing, without bypassing. But even if you are not bypassing it at higher frequency, the source regeneration effect may go away or it will get suppressed. The similar thing is happening here. So this has to be, kept in mind. Exact derivation can be done, showing the parasitic effects. You can derive the exact expression in terms of CGS, CGD, etc. That comes like, the complete expression. And from there also you can conclude the similar thing. But just, the basic idea you should have. So the question that I started with was what? The question that I started with. So everybody is clear about this common mode gain issue?
Yes, sir.
So how do you improve the common mode rejection ratio, or how do you reduce the common mode gain? Generally, what are the ways? How do we increase the common mode rejection ratio? That means how do we reduce the common mode gain?
By increasing the length of fifth M5, sir. Like it would increase the um
Length of
early,
M5. So, L5, if you increase the L5, RO5 will increase. As a result, source regeneration will increase. So if you're having the source regeneration resistor increasing, the gain will drop. So effectively what you're doing by making the M5 length larger, you are making it closer to the ideal current source. So larger is the length, the channel length modulation will be lesser. As a result, it will become less dependent upon common mode signal. Because what happens when you have the common mode signal? So if you have a common mode signal here at the gate, it will lead to some common mode signal at the source, right? It will pass some signal to the source. This gate voltage is anyway fixed. Effectively, the common mode signal, it will lead to a signal change at the source. But if because of this signal change at the source, you're not changing the current much, current is remaining constant, independent, unaffected because of this signal, then you have a good current source and you are not going to get much signal at the output. Because only because of this drain signal getting changed, if your current changes in M5, then it will lead to change in the output signal. Otherwise, it will not lead to. So with the ideal current source, completely ideal current source, it will not have any change. Whatever be the voltage at the gate, common mode voltage at the gate, it will not have any change. As a result, output will also not change. So in order to make it more ideal, you make the L larger. But again, that larger L will also have more parasitic. It will also, have a trade-off that, this point will come earlier. This particular point will start coming earlier because the parasitic is increasing. There is always a trade-off. And if you want to make it cascode, another option is you use a cascode current mirror. So rather than putting one, you put, two of them like this. So then the impedance is GM RO squared, GM RO times RO. You know the impedance looking into the cascode mirror. What is the impedance? This, right? So this is a small signal resistance of cascode mirror. So if you don't remember it, try to derive it. I think you might have studied these things, right? So all of you, how many of you know this is the small signal impedance? Those who have attended some of the lectures in the semester, I did not take many, but whatever you have attended, some parts I had discussed. How many of you know that this is the value? Okay. So most people, it seems they know. So how come in this case it is showing in this meeting 34 people, but the number of raised hands I'm seeing only 15, rest of them 18. The rest of the people don't know. So the rest of the people might not have attended earlier session in the semester. So anyway, these things we will try to. I think in one of the lectures that I had given in the recording, NPTEL lectures, they had all these derivations? Anybody can remind me?
Yes, sir.
Then the people who are not raising hand, they have not gone through the lectures. That's what it means. All of you have gone through the recordings of the NPTEL lectures, whatever I had recommended. Sambhav
Yes,
De, Mr. Sambhav De, can you unmute yourself? Sambhav De.
Yes, sir.
So do you remember, have you gone through the lecture?
Yes, sir. I went.
So do you remember the derivation, like cascade current source? What is the output impedance? The thing I have written over here, do you remember? Yes, quickly, I mean, we don't have so much time. Do you remember or not? Like, have you studied it somewhere in the lectures?
I studied, but now I'm fine.
So then what is the point of studying if you don't remember? So these things are the basic things, this you have to remember in order to be able to design anything. So then I will not repeat it because it is already covered in one of the lectures. So going forward, you have this. So generally now, if I do this, common mode gain will reduce, but what is the disadvantage? Let me check. Let me ask people, and that helps me in gauging the condition. Where are the people? People are here. So let me ask Maitra Das. Maitra Das, unmute yourself. Maitra Das,
Yes, sir. Yes, sir.
can you explain what is the disadvantage of doing this? This is cascade. Whatever I have done here. Yes, any disadvantage?
Sir, I think the voltage swing will decrease.
Voltage swing will decrease. Which voltage swing will decrease? Where the voltage swing will decrease? Yes, anybody else who can explain better? Answer is partially correct, but he's not able to answer where. What swing will increase, reduce? Anybody else can answer?
Sir, does the ICMR reduce?
Yes. So the ICMR, what is ICMR? I've already given you in the question in input common mode range. So why will ICMR reduce? Yes, why will the ICMR reduce?
So because the source,
Because
minimum
if you
source
use a
voltage
cascode
required,
current,
Yeah, earlier if you had only one device, the minimum source voltage, minimum, V in CM min is divided by what? V in CM min, V in CM min. That means the input common mode range, the minimum value of the input common mode voltage that you can apply will depend upon VG S1 plus the VDS of M5. Earlier only this was the case. And because you need a VGS of M1 and you need certain VDS of M5 so that both are in saturation. So V in CM will be decided by these, and we have already discussed how to reduce this. So this is dependent upon VT plus V overdrive VT of VT5, or sorry, VT1 plus V overdrive of 1. And this is dependent upon VG. So VG, this minimum value is VG5 minus VT5. And both these values can be increased by increasing the W by L of M1 and M5 that we discussed yesterday also. But now you have another transistor, you call it M8. And therefore now you need to take care of VDS of 8 and VDS of 5. So now it will be, the modified case, it will be VGS1 plus VDS5 plus VDS8. Because now the VDS 8 also needs some voltage to remain in saturation minimum. And then VDS5 needs something. And then VGS1 needs something. So these three will come in picture now. So now, therefore, definitely this term is smaller than this term. Therefore, the minimum value the V in CM can get is going to be higher in this case, and which you are going to reduce the common mode range. Why the common mode range is important? Why the input common mode range is important? We are talking about differential signal. So why do we worry so much about common mode range? Yes, anybody? Input common mode range, because ultimately we are worried about differential signal. Input signal is the differential case is anyway small. We are always simulating with small signal AC. So why are we so much concerned about having good common mode range or reduction in the common mode range, input common mode range? Anybody?
So we get good amount of gain in this region.
In this region means which region?
In the common mode, in the region where the slope is high. When you vary in the input common mode,
Which region slope is high, and I'm not sure which point you're talking about. Which region? Once again.
sir, when we vary input common mode and check the value of V output, so the region where we get the slope high, we try to keep the biasing point at that region.
I don't know what does that slope has to do with the signal here. So if you vary the common mode signal, you will get some slope in some region. After that, you will in that region you're having more effect of common mode change. But how does it relate to the differential operation? So what I'm saying is, even for ultimately we are operating this amplifier in differential operation. So we are interested in differential operation, differential signal. So why are we worrying about the input common mode range? We know that for certain input common mode, it will not work. There is some minimum input common mode voltage required, and there is a maximum common mode input allowed. So beyond that, you cannot operate. If you take the V in CM lower than, if you take the input common mode lower than the minimum required, the amplifier will not work. Likewise, if you take it much higher than the maximum input common mode allowed, again the amplifier will create problem. So why are we concerned about the common mode input? Like ultimately, we can bias it with the DC value VDD by 2 and then operate it with small signal AC. Why are you worried about common mode voltage and having a large range of the common mode? Are you getting the question? Previous exercise, what did I tell you? I told you to bias the input devices with some DC voltage 0.5 volt, which is close to VDD by 2, and then apply some small signal AC. If you are worried about only the small signal AC, then why are we so concerned with the common mode range? Input common mode range. Yes, anyone? No one. What is this? What is this?
It's an unity gain buffer, sir.
So in this case, if I use this amplifier to construct this, for what input values you will get output following input? Ideally, this should be the case. But in reality, what will be the scenario? In reality, what will be the scenario?
So until and unless all transistors are in saturation, it will not exactly follow the V out, right? Because so it should
So
lie
what will be
within
changing?
the
What will change in this curve?
in the lower part from 0 to a certain value, it will not be a straight line.
What will it be? if the positive input is very low, what will happen?
Device will not turn on.
Sorry, louder.
So the device will not turn on. It will still be off.
Turn on. So what will happen to the output?
0.
0 will remain 0, right? Because if you put 0 here, this one will be close to VDD. This is switched off. This is on. This will be close to VDD, and this will be turned off. As a result, this is turned on. This is the bias voltage. This will pull it down. Drain voltage will be 0. Is that clear? So for some values, it will remain ground, and then it will start increasing, and then it will become follower, and then after a certain value, again it will deviate because the upper transistor will intend to triode. So this range is of, if your input common mode range is less, this range, desired range will be further reduced. It will shift upward. For differential operation, feedback loop, whenever we are operating in feedback loop, we would like the amplifier to be able to handle the common mode signal, like the input common mode range signal should be good, so that in the feedback loop, whatever be the DC level of the signal, it is able to operate. Because DC level can be any value. So in order to have full range, we should be able to deal with the entire DC range. So especially for this case where you have a voltage follower and the signal can have any value. In case the signal is known to have very small value, then you don't need to worry. So where you need to worry about common mode range, input common mode range need to be checked. So in some application, for example, if you're talking about, say, an input front-end amplifier. Front-end amplifier is supposed to amplify the input signal coming from a sensor. So there, the DC biasing is fixed, right? You have fixed the DC bias with some mechanism, and then you are applying a small AC signal on the top of it. There, we don't need to worry about input common mode range. So where the input common mode range will be important needs to be checked. Whether for this amplifier, we need a large input common mode range. It is not that everywhere you will need large input common mode range. For you may have amplifiers in later stages, especially when the inputs are already amplified. The inputs have now become a large signal relatively, and then you are having blocks like voltage followers, etc. There you will need large input common mode range. The amplifiers which are very early in the series, like just close to the sensor and receiving very small signal, there we don't need to worry about input common mode range. That much we should decide that at what stage, in which case common input common mode range is required, in which case it is not so much required. So in case common mode range is not required, then we will optimize other parameters. We will sacrifice input common mode range. Like the input stage, very important to reject the common mode noise. So we will be happy to include this cascode and have a better common mode rejection, because there the input common mode range is not important. But for a voltage follower, input common mode range is important, right? Any question before we proceed further? So we are talking about the high frequency poles, and somebody rightly mentioned that the high frequency poles are, at the drain of this B and C. And A, you already have a low impedance node, because at A, the small signal resistance is small, right? So 1 upon GM3. So the source node over here, that is the drain of M5, it is the AC ground. We don't worry about the pole at this point. So mostly the poles at A, B, and C are of concern. At A, we see that it is a low impedance node, whereas at B, the impedance is RO, RO4 parallel RO2. Likewise, at C, the impedance is RO6 parallel RO7. So now these two are therefore comparable. Both of them has comparable RO. And the capacitor, overall capacitance also may be getting comparable. So at this node, the parathetic capacitance for B also may be comparable. So therefore, this becomes a problematic case, because now you are having two nodes which are having critical poles, and that will lead to more stability problems. So have you studied the Bode plot of two-stage amplifier? How will it look like? Or in the
Sir,
feedback
and the
system, have you studied? in the feedback system, you might have studied frequency response or two-pole system. Two-pole system means you have two critical poles. So how does it appear?
At every pole, the
How
amplitude
do you
falls off at
model?
20
First of
dB
all,
per
what will be the
dipole.
expression of a two-pole system? A naught upon 1 plus S upon P1,
It's about
1 plus
into
S
1
upon
plus.
P2. So P1, P2 are the poles. In this case, the P1, P2 will be the two poles of the amplifier we just discussed. All of you have studied this frequency response. I think, did you find this in my lectures, earlier lectures regarding?
Yes, sir.
Yes, right?
Yes, sir.
So then I should not go into too much detail. So you will have two poles, P1 and P2. Those who are not going to the lectures, they are doing, they will eventually drop out of the course because some things which I have given you to study, you are supposed to be ready with that. If you're not seen those lectures and come here, some things you will not understand because I'll just rely on those videos. I'll not repeat everything. So this, in this case, P1, P2, what do we get? At P1, it will start dropping by 20 dB per decade. At P2, it will start dropping by 40 dB per decade, minus 20 dB per decade, and here minus 40 dB per decade. And what about the phase response? Phase response, how does it look like? This is your magnitude, dB. What about the phase? How does the phase change at P1?
45 degree, it changes by each pole.
45 degree. If you go past the first pole, if your omega is becoming much greater than P1, what will be happening to the first expression? It will become 1 upon iota omega upon P1, right? Because you can ignore the 1. So you can ignore the 1 because now this has, omega is much greater than P1. So in this case, it is much, you are much beyond. Sorry, I just wrote the opposite. So the first expression, what will happen to it? 1 plus S upon P1. So here is 1 plus iota omega upon P1. Now, once your omega is much greater than P1, you are way past 1. As a result, you will write 1 upon or P upon iota omega. And this will be, if you multiply up and down by iota omega, it will be minus, iota P1 upon omega. So what is this minus iota?
Minus 90 degree.
So this is e to the power of minus iota pi by 2. So at far away from P1, the phase will change to minus 90 degree. Well, 0 from if you are taking it from 0. And then exactly at P1, it will be 45, minus 45. But far away from P1, it will lead to a next shift of minus 90. And P2 again, likewise, far away from P2, that means asymptotically it will reach minus 30. Ideally, it will never reach, but asymptotically it will reach minus 80 because the two poles combined together, you will get e to the power of minus iota pi by 2 minus iota pi by 2 e to the power of again I have this pi iota pi by 2 is something like again e to the power minus pi iota pi by 2. Two magnitudes will be coming and taken together minus 90 degree minus 90 degree will get 360 degree because just like I have done for this one, the second one will give you also similar expression iota omega upon P1 iota omega upon P2. So again iota 2 times and you will get this overall. So ideally it will happen at a very large frequency, but practically, if you go far away from P2, it will start approaching 180 degree. Therefore, here, if you have to have a good phase margin, how do we look at the phase margin? What is phase margin?
That's the point at which the frequency at which the phase will reach my minus 180 degree. The difference in the frequency at which the phase will reach minus 180 degree and the gain will reach, and there will be unity gain.
No, that is not. So you need to first of all look at the 0 dB point. So in the gain, this is suppose there's a 0 dB point. 0 dB means the gain is 0 dB. So the point at which the gain reaches 0 dB. At that, what is the phase? So if that phase is greater than 45 degree, that means you have, because this is a overall amplifier feedback, you will get another 180 degree. So now if you get a phase of 180 degree at this point, or greater than 180 degree, in the overall closed loop, it will become 180 degree plus another 180 degree. That means it will become unstable. So here, when we go to, when we have two poles, there is a possibility that while the 0 dB point occurs, the phase has already shifted close to 180 degree, and therefore you don't have much phase margin. Right? For a feedback amplifier, we will have, the phase margin equal to 180 degree minus whatever P as a function of omega modulus. That means as compared to 180 degree, how low it is. If it is coming closer to 180 degree, that means you have less margin left, because in the closed loop, it will become 360 degree. So I need to make sure there is enough gap. Ideally, it should be, greater than, it should be greater than 45 degree, or some people keep it 60 degree, something like that. But here we are seeing that after the second pole, there is a possibility that it may touch, or it may come very close to 180 degree, which will lead to very less phase margin, and that will lead to unstable behavior, oscillatory behavior. But so, and in this case, you can also have the two poles pretty comparable, pretty close, right? So in this case, the two poles, if they become pretty close, that can also lead to problems, right? So if you have, the two poles coming very close, what will happen? It will start dropping immediately at minus 40 dB per decade. Suppose the two poles are coinciding, and then the drop will be very sharp immediately after that pole P1 equal to P2. And then the phase, how will it look like? So right after P1, it will, very quickly shift to minus 180 degree. And as a result, very soon, you will get a condition where the phase margin is at, in fact, at, 0 dB omega, sorry, that omega 0 dB, that means the frequency at which the unity gain is coming, the phase will be very close to 180 degree. So here, because the poles are comparable, and if they become close, the gain will drop with minus 40 degree per decade very fast. And then the phase will also drop to minus 180 degree very fast. As a result, at omega 0 dB, you have very less phase margin left. Very, it is almost close to 180 degree. Therefore, you don't have much phase margin left. As a result, it will lead to unstable response. Is this clear?
Yes, sir.
Yes. Any question? So now people do, in order to stabilize this op-amp, what do? They will put a cap. Let me put a cap. So that's called Miller compensation cap.
There will be pushing the pole to the right, like P2 to the right, using the cap.
Yes. So let me first draw this. Now, if I have, say, why is it not selecting? Now, the people, the way to compensate is there is a compensation capacitor CC added between output of the first stage and output of the second stage. There is a common way. So what is the implication of this? Why do people do this? So in this case, because you have a gain, right? So the second stage you have a gain, and that will lead to Miller effect. And as a result, you will get a effective, load effective capacitor over here, CC dash, which is quite big. Other side, you will not get that big. This is, close to CC only. And then there will be some load capacitor CL also over here because of the next stage. So this CC dash is going to be bigger than CC, right? CC dash much bigger than CC. As a result, now the first pole has been pushed towards lower frequency, and second pole it will not be affected much. At least here we can see that. But actually what happens is at lower frequency, at higher frequency, this also gets shifted towards higher value. Why it happens? Because this CC, it basically creates a low frequency or basically a low impedance path for the CGD of 6. So whatever signal change is happening here, it will try to couple it with the gate. So basically there is a 1 upon omega CC being formed, and that basically creates a kind of, short circuit kind of scenario for the CGD, and that leads to basically reduced impedance. Effectively, it becomes equal to 1 upon GM6. Again, that requires the detailed analysis to justify. I'm giving you just hand-waving argument, but I will not go through the detailed analysis and detailed derivation right now. It will take a lot of time. But what I'm saying is this phenomena is called pole splitting. So the first part is easy to understand, that it will definitely push the P1. P1, because of this node, it will push it down because the capacitor, Miller capacitor is going to be big here. CC dash is going to be big here. Other part, if you assume that the CC is anyway remaining similar, so Miller, because of Miller breakup, if you do the C here, the capacitor will be similar to CC, and CL is already there. So here it has not changed much. But what I'm saying is, in actual scenario, it actually shifts towards higher frequency. But even if you assume that it is not changing much, we are definitely sure that P1 is going to go higher. So what is the benefit of doing that? Now, earlier, maybe your curve was something like this. Now, the modified scenario, how is this curve going to look like? Modified scenario, it will something like this, and it will be going down from here. And then, you may have the condition, as I'm saying, that the second pole also gets further higher. And why it gets higher is because effectively your small signal impedance so when we are talking about high frequency, like at these frequencies, very high frequency. So at very high frequency, what will happen to the CC? CC will create a 1 upon GM effect. So because the CC 1 upon omega CC will be shorting the CGD of M6. Therefore, it will become like a diode connected device. And as a result, its impedance will be reduced, right? At a lower frequency, its impedance is, 1 upon RO6. So here it is 1 upon RO6, but here it will become close to 1 upon GM6. Sorry. Not 1 upon RO6. It will be RO6. So at lower frequency, the impedance is RO6 parallel RO7. I'm just talking about RO6 right now. At higher frequency, because of the CC, 1 upon omega CC becoming larger, this will try to become close to 1 upon GM6. As a result, what is happening to the overall small signal pole over here? 1 upon omega. What is the omega 2? Omega 2 will be 1 upon GM6 times whatever CL plus CC approximately. So what we are having is, because of this shorting effect of CC at high frequency, the impedance of the output stage drops at the high frequency. As a result, what will happen to the pole? It will shift towards further, higher frequency, right? And the ideal case is that the shift is such that the crossover point or the second pole comes beyond the zero crossing or at the zero crossing. So here what I've done is I've shifted the two poles. P1 became lower, this P1 dash, and P2 dash I shifted to this point. After P2 dash, there is a minus 40 dB per decade. Now, if I have made the P2 equal to omega 0 dB, that means the P2 is coming at or after omega 0 dB. That means zero crossing point, the crossover frequency at which the gain becomes 0 dB. What is the benefit of doing this? What is the benefit of doing this?
If I have my zero crossing point further away, so this will ensure that the point where my gain is unity, at that point my phase is not minus 180 degree, but significantly less than minus 180 degree. So the phase crossover point is later than the gain crossover point. So
yes,
this
so
will
basically
ensure
at P1, what happens? P1 we get a net exactly at P1 it is minus 40 degree, 45 degree, and then at exactly at P2, what is the phase? Minus this is far away from P2 we get minus 90 degree. Sorry, Far away from P1, we get around minus 90 degree. Exactly at P2, we get another minus 45 degree, minus 135 degree. And after that, far away from P2, it will be approaching minus 180 degree. But now here, if the P2 is equal to omega 0 dB, what will happen to the phase margin? PM will be what? P1 will be 135, 180 degree minus 135 degree, right? 180 degree minus 135 degree. So you will get at least 45 degree phase margin. If you go higher than that, it will be further better. So it will ensure that your phase margin is higher than 45 degree. So that is the benefit of this compensation scheme. So it is called pole splitting. The pole has been split. The lower pole has been shifted towards lower frequency. Sorry, the first pole has been shifted towards lower frequency. And the second pole, which was also earlier, it was close to the first pole, it has shifted to higher frequency. As a result, your phase margin is improving. And in the feedback loop, in the feedback operation, the amplifiers will be more stable. Is that clear to everyone? So this scenario, it basically requires a compensation cap and the pole splitting mechanism because it has two dominant poles. Is that clear to everyone? I should not say two dominant pole. It has two critical pole, two high frequency poles, and one of them we not want to make it them dominant. So the way to make it dominant is, the P1, because of the Miller compensation, it is getting much bigger cap, and as a result is shifting down. The P2 is shifting up because at high frequency, the CC is having a shorting effect, and that is reducing the impedance. As a result, the P2 is shifting, down. And then we make P2 beyond the omega 0 dB, greater than or equal to omega 0 dB. And as a result, the phase margin is ensured to be higher than 45 degree. Is this clear to all of you? Any problem? Okay, so therefore, this scheme has this disadvantage of compensation capacitor. And secondly, at advanced nodes, the variation in P1, P2 may be significant. So there is another issue over here of zeros. So another zero also comes into picture. But I will not go into that detail right now. And especially because we are probably not going to focus so much on this op-amp. We will be using another op-amp topology which does not have this problem. Because at advanced nodes, all these compensation schemes become more complicated. Variations are more. People still use this scheme, but we will use an alternate scheme where this problem does not occur. So let us look at that alternate scheme. So this is called Miller compensation, whatever we just discussed, Miller compensation. Because we are taking advantage of Miller effect to split the poles, push the dominant pole towards lower frequency. So let us look at the scheme 2. I think there is power is going to go. Are you able to still hear me? Yes, sir.
Yes, sir.
Yes, sir.
This is your differential amplifier with current, the diode connected load. We have discussed this yesterday. So the gain from the first stage is not going to be much. So in this case, what is the gain? I'm telling you, this is the output, single ended output. What is the gain? Assuming that the sizes are same, M6, this this M6 equal to M3 and M4 equivalent to M8. Likewise, M7 equivalent to M9. What is the gain?
GM2 by GM4 multiplied by GM8 R8 parallel R7 R8 parallel R9.
What? Let me see. The GM2 by GM4. Then
Sir, this GM8 multiplied by R8 parallel R9.
R8, RO8 parallel RO9.
Yes.
Anybody else? Yes, anybody else? Yes, anybody else having any suggestion? Is this correct? So what he has done is that you've got the signal at one side. So whatever the signal, if you assume the half circuit, if this is AC ground, if I assume this, this is AC ground, then whatever VD you are having, VD by 2 will appear here. VD by 2, if I this is assume this VD is VD by 2, differential signal by 2, half of the differential signal. And as a result, you will get the stage 1 gain given by GM2 by GM4 into VD by 2. That signal is appearing at the gate of M8. And therefore, the gate signal over here, this is something like this multiplied by the input signal. And therefore, that multiplied by the gain of the second stage is writing GM8 times RO4 parallel RO9. What is missing? What is missing? Anything missing? Yes. I tell you something is missing. What is missing?
So the drain voltage at M7 is varying, so I think we should consider its effects on M9.
Yes.
So
So one signal is here, but other signal is here also, right? So here also you are getting that signal. And as a result, this is also going to produce. So what is the gain of the second path? Suppose this is minus VD by 2. What will be the gain of second path?
So that will be GM1 by GM3 multiplied by GM6 by GM7, right? Because the seventh is drought connected.
GM6 by GM7, okay. And we have to look at the output, right? So it's not the final output. We have to go to the output. You have given me the gain only till this point. Yes, can you complete it? Who spoke just now?
Yes, sir, I did, sir.
Complete the thing.
Then, sir, again, it will be from the gate to the drain. Again, it will have a gain of GM9 multiplied by R8.
Multiplied by
GM9 multiplied by R9 parallel R8.
GM9 into RO9 parallel RO8. This is the second path, right? From here, you are calculating the gain to this stage, and then this, whatever gain you are getting, that same signal appears here, and from there you are getting another signal output. Basically, you can take the superposition, both the things combined together. Ultimately, here, if I already mentioned that GM4, M4, M8 are same, so this will cancel out. Likewise, in the second path also, I have mentioned M3, M6 are same, so this will cancel out. Also, I have mentioned M7, M9 are same, cancel out. Ultimately, GM1, GM2 are also same. So ultimately, you are left with, overall gain of GM1 RO8 parallel RO9 by, into 2. So basically, GM RO. Is that clear to everyone? So you have to look at the half circuit, both the paths. Ultimately, what is happening? So plus VD by 2 is going to lead to delta I small signal here, minus delta I small signal here. So DC condition, both the currents are same, right? So this DC currents are same. But because of the plus minus VD by 2 small differential signal, you get delta I on this side, delta I minus delta I on this side. So now, if you look at this carefully, M3 and M6 are forming current mirror. M3 is a direct connected device, M6 is mirroring it. So whatever small signal comes here, minus delta I will come here. Likewise, M4 and M8 are also forming current mirror. Whatever delta I comes in M4, the same delta I will come here. Now this delta I minus delta I comes here. This M7 is that connected device, and it is forming current mirror with M9. So M7 and M9 are forming current mirror. So whatever minus delta I comes in M9, M7, the same will come in N9 minus delta I. Therefore, the net, if I look at the net impedance here, which is RO9 parallel RO8, net current going into the output will be 2 delta I. And that delta I is, GMVD. And therefore, the gain is this GMVD times RO8 parallel RO9. Is that clear to everyone? Yes, any question? Remember that if you change the ratio, right now I have made the ratio same, 4 to 8, 3 to 6, 7 to 9, all these ratios are same. If I have a ratio, like there is a K ratio over here between M4 and M8, M3 and M6, then accordingly that factor will enter, because if the ratio is changed, then the current mirroring ratio will not be same any longer, right? So apart from the RO, GM of the first stage, RO of the second stage. Apart from that, the ratio will also matter. If the ratio is same, then this is the expression. But if your ratio is increased, suppose you wanted to have bigger gain, and therefore you wanted to increase the RO of the second stage, so increase the length of M8 and M9. What will happen? Will the gain increase? Yes, will the gain increase?
So can you repeat the question once? That is, we are only increasing the length of 8 and 9.
Yes, because my output RO I want to increase. So if I just increase the length of 8 and 9, what will happen?
So if we increase the length of 8 and 9, then the mirroring between 4 and 8 will not be proper, right? Because the W by L ratio between 4 and 8 will change. Then we will not get this gain.
Yes, basically, if you reduce the DC current in M8, the factor of K, you are reducing the bias current in M8, and therefore the RO is increasing. But the current mirroring from 4 to 8, the small signal current mirroring, that will also be reduced by the same factor. Therefore, you will not get any benefit. Is that clear? Because the small signal delta I will become K times delta I. If the K is, in this case, K is less than 1 because you have increased the L. So the W by L ratio of 8 is lesser than M4. Therefore, the delta I times K will appear here. Therefore, that will reduce the gain. That will not reduce because RO has increased by K, so it will cancel out the effect. It will not have much benefit. Is that clear? So what will you do? You have to increase both W and L. If you increase both W and L of 8 while keeping the K unity, so the mirroring ratio remains same, but you are increasing both W and L. Then the mirroring ratio is same, K is remaining same, but your output side, once again, what is happening? So if you keep the W and L both large, what will happen? Bias current, DC current at the output stage, is it increasing? Decreasing? What is happening? Yes, quickly. People are
change, sir.
sleeping or what? Yes.
It will not change, right?
It will not change, right?
because
The K is remaining as long as I keep the unity K, that means W by L ratio same, the bias current has not changed. But what has changed? L has changed. If L increases, what happens? RO increases. As a result, the gain will improve. Is that clear? The RO is what? 1 upon lambda ID. ID is same, but lambda is dependent upon inversely upon L. If you increase the L, the RO will increase for a given current also. So as a result, just increasing the W and L of 8 and keeping the ratio same, that will increase the gain for the output stage. Is that clear? RO will increase. And then second option you have is GM. GM of the input stage you can increase. Therefore, the GM1, GM2, you can keep it high. How you keep it high? Keep the W large. You can keep the L minimum because the RO of the first stage doesn't matter. So, RO1, RO2, RO3, RO4 don't matter. So I don't need to have large length here. I can keep the minimum length and get maximum GM from the first stage. That is by increasing the W by L of the first stage. The input devices, for larger gain, you can increase the W1 and W2 likewise, and you can keep the L1 minimum. This will be minimum. Likewise, the length of N3, M4 can be kept minimum also. But then for the output stage, I will keep W8, W8 and L8. I will keep it both high so that the RO is higher. And the same thing for the other side also. So M9 also needs to be increased. RO of 9 should also be increased. The same thing will happen for RO9. So for that, M9, W and L should also be increased. Is that clear? Again, the length of this stage doesn't matter, 6 and 7, because here anyway the RO is not coming into picture. So M6 and M7, the L can be minimum. But the output side, M9, I'll have to increase the W and L so that the W by L ratio with respect to M7 is maintained, but the RO is increased. Is that clear to everyone?
yes, sir.
In this circuit, what is the critical pole?
So there is only one critical pole since at the V out, because all other
Yes,
nodes
if
are
I
low
talk about the
impedance.
pole, these are low impedance node 1 upon GM, 1 upon GM, 1 upon GM, because here RO parallel, RO down, R up parallel, RO down, right? So R up is RO, but R down is 1 upon GM. Here also 1 upon GM, 1 upon GM. RO at the net impedance, small signal impedance at the node 3 is what? R up is 1 upon GM, R down is 1 upon, R down is RO1. So RO1 parallel 1 upon GM3 will be approximately 1 upon GM3. Likewise, the small signal impedance at this node is also 1 upon GM4. So these are all low impedance nodes. Only here you are getting RO. So the net impedance here is RO. Therefore, this is only the critical pole. Others are anyway having lower, you are having lower impedances. But now the gain in this amplifier is only GMRO that you are getting in single stage also. So gain point of view, it is not as high as, it is definitely much poorer as compared to the previous topology that we discussed. Right. So how do we change that?
So like in the first stage, instead of keeping the PMOS, two PMOS diode connected, if we can introduce a current source load, then it will increase again, right?
But then the same problem will come, right? So you will not have the the poles will be both nodes. Both nodes will have poles.
Yes, sir.
Again, you have to compensate. You have to do the compensation capacitor, etc. So one way is to use the cascaded output state. So let us see, how do we cascade? Now at this point, I want to introduce a cascade state. That means I want to do something like this. With appropriate bias voltages, VB, P, VB, N. So in this case, what will be the gain? Others are all remaining same, other things are remaining same. What will be the output gain in this case? Up to this point, the story is same. Whatever current you are getting, differential signal, that is remaining same.
So the current will be boosted by the intrinsic gain of the two masses.
Sorry,
So the current will be boosted by the intrinsic gain of the two masses.
current will be boosted. What do you mean by current will be boosted? The
So
MOSFET will
now
change the
instead
current.
of GM,
Sorry, sir, not the current, means the equivalent impedance that will be boosted due to the two masses.
so now instead of GMRO, I will have GM multiplied by GMRO square, like of the order of GMRO whole square. Half GMRO whole square.
Yeah, so ultimately see, means if I look at this as a AC ground, assume, forget about the differential operation for the time being, you have VD by 2 here. So again, you have, GM VD by 2 flowing. GM VD by 2 flowing. So again, I call it GM1 VD by 2. So the same current is here, GM1 VD by 2. Again, mirroring same, so GM1 VD by 2. The same current is flowing here. Earlier, I had put a small impedance over here. Overall impedance over here was how much? RO1 parallel RO2. In this case, what is the impedance at this node? In this case, it will be, because whatever small signal current comes here, this is in series. So the same small signal current will come here. This one also will be GM1 VD by 2, because series connected MOSFET will pass the same small signal current. So putting this transistor in series will not affect the small signal current. It will have the same small signal current flowing. But now at this node, if I talk about the net small signal resistance, what is that net small signal resistance? What is R down? What is R up?
So they are of the order of GMRO square.
Approximately, this is, if I call this, I don't know what was the number. Number was, so this was M9 and this was M8. So I will call it M10 and I will call this M11. This is M9 and this is M8. So R down, it is going to be GM10 RO10 times RO9. And R up is also GM11 RO11 times RO8 approximately. This part you remember, like this is the derivation given in earlier lectures also. Impedance looking into the drain of cascade devices, M10 and M9. So whenever you have MOSFETs like this, you have two MOSFETs connected like this, you can do the small signal derivation. You can arrive at this. The gate voltages are fixed, VG1, VG2, DC voltages, and you try to find out the impedance looking into the drain of this kind of structure. Two MOSFETs in series. That will be GM1 1 RO1 times RO2 approximately. That is same as, if you have a MOSFET with a source regeneration resistance RS, gate voltage constant VG, V1. Looking into the drain, the impedance will be GM1 RO1 times RS. In this case, RS has been replaced by RO2. That's all. So you can do the small signal analysis and find out. If you're not remembering, you can derive it easily. You will get this. So now the net impedance here is large. And as a result, the current will get multiplied by this whole thing. So now the gain will be GM VD by 2, or basically first let me write. The 2 term will go away because you have both sides coming, combine them together. So you will have basically GM 1 times GM of the second stage, basically the inverter, the M11 and M8 here, M10 or M11 times RO10 times RO8. So just in terms of order, if you have to just write the order, assuming that RO, we are just looking at of the order of gain. So GM1 times GM10, GM RO10 times RO9 or any one of them. So if I assume all are similar, this is GM RO square. So the order of gain becomes similar to what you were getting in the previous case. So now in this case, what is the pole scenario? So first stage anyway, still these are low impedance nodes. We don't get significant pole from here. These are all going to be high frequency, at very high frequency, because these are low impedance node. 1 upon RC constant is high frequency. What about the output node? What has happened to this pole?
It will shift towards higher frequency.
Higher frequency.
No, lower frequency.
Lower frequency because the impedance has become much higher, right? So GM RO times. Earlier it was RO, now it has become GM RO. So GM RO may be 100. Now this pole has shifted further towards lower frequency. Therefore, bandwidth point of view, definitely you will have a trade-off because your overall bandwidth will be limited because you are having a larger impedance at the output. That is true. But then you don't have to put a compensation capacitor. In that case also, although you are not having a RO square impedance, GM RO square impedance anywhere, but you have to put a compensation capacitor and that also reduces the bandwidth. Here, the output stage is cascaded. So because of the GM RO square impedance, the bandwidth will be lower, but you don't have to put any compensation capacitor. You don't have stability problem as such. What about these nodes? These are the additional nodes that we have introduced. Yes. Any problem with these nodes? What is the net impedance looking at this node?
They will each give around RO by 2.
RO by 2, because if you have, say, NMOS transistor with a load RD and gate voltage is suppose fixed AC ground means some DC voltage, and you're looking into the R in, looking into the source. What is the impedance? Small signal resistance approximately?
Sir, 1 by GM plus RD by GM RO.
Approximately it will be RD upon GM RO. Right? So in this case, what is RD? If I look into any one of them, if I say look into this, what is the suppose I call it node X. So what is R up at X?
GM RO square.
Because R up this RD equivalent, there it is something like, GM RO square, because looking upward, this impedance is coming, this, which is GM RO square. Therefore, divided by the GM RO. Therefore, it is of the order of RO. So now these two impedances are also significant. They are RO. They are no longer 1 upon GM. These are also RO. But still, at the output node, it is GM RO times RO, GM RO square, much bigger. And secondly, the load capacitance will also come CL which will also be significant as compared to the capacitances here, which are just parasitic capacitances. Because of these two factors, it will be self-compensated, because it has only one dominant pole. Other poles are much higher than the dominant pole. So you will not need even if you need a compensation capacitor, you need to put it here only. You just put it at the output. There is no Miller compensation required because this is the output node. This is the dominant pole. You just put some more capacitance if there is a stability problem coming. So the Miller compensation is not required, and there are some complications associated with the Miller compensation also. It leads to, as I told you, it leads to a zero path, and that complicates some of the sizing issues. Here, that Miller compensation is not coming. You're not using a capacitor in series with gate and drain of the second stage. That leads to simpler compensation. You just put a capacitor, additional capacitor at the output in case your phase margin is not enough. In case the load capacitance is very small and you want to compensate it further, you just add some capacitor at the output point. Is this clear?
Yes, sir.
Now, how to bias these two stages? That is also another question. So very quickly, before we conclude, we can discuss the biasing. Only thing is I have to delete this whole thing, or basically, copy from somewhere. So if I copy from here, because eventually it becomes very dirty after drawing. So copying, redrawing everything again takes time. So copy and okay. No, I did the wrong thing, but anyway, so we can just delete this part and modify the output state. So if I have to now bias it, what are the ways? So I will just, this is the PMOS and this is the NMOS. So one way to bias it is that whatever bias current you're having here. So remember that, at wherever points the wires are connected, I will draw this dot. Other places, if I'm not drawing this dot, wires are not connected. So if it is a crossing point and the wires are just passing over each other, I will not draw this dot. So now if I take this, whatever gate voltage of M6 is there, I will bring it here. Here it is not connected. So here I have not drawn the dot. That means it's not connected. So remember that. I can put a jumper, but jumper becomes a little clumsy and doesn't look good. Generally, this is the practice. So wherever there's a crossing point, you put a dot. When there is no crossing point, don't put a dot. So now I can use a current mirror structure like this. Now this can be used to bias this gate voltage. Why? Because now here, if you see, if I am sizing this M6, after that, suppose this, I call it M12, M12, M13, M14. If I am, suppose W by L of this is, half of W by L of M5. That means whatever bias current you are having here, I bias, you will have I bias by 2. This will also have I bias by 2. These two on the upper side are also having I bias by 2. This is also having, provided the ratios are same, I bias by 2. Therefore, now the VSG of M4 is appropriate. It is going to match with the VSG of M8, I bias by 2. So VSG are similar. And therefore, you are going to get, when we have another MOSFET in series with M3, this is also diode connected. This will also have VSG. And that again can be applied to this one. So these two branches will get matched. So this can generate an appropriate gate voltage for this transistor. And we call it M whatever 10, M11. Likewise, how will we create the bias for M10? Yes, M10.
So from M6, we can take another line and then we connect it to the NMOS and then diode connect the NMOS and then put another diode connected on the top and then connect it to the M10.
Yes. So you can take it from anywhere. You can you can take it from here also. You can take another PMOS, and now this is going to have same VSG as M14, and then you bring it down. Then you do put two NMOSes over here. Let me draw it a little bit further apart, or I have to delete something. So I will take it here. And then I will put two NMOSes. Now same thing will happen because now this is also I bias by 2 because this is also mirroring whatever direct connected MOSFET M14 is having, it is mirroring that because these two are forming current mirror, right? So
Sir,
now,
one thing, sir. Hello.
sorry,
Sir, you have connected M6 and M12, right? So either of M6 or M12 must be diode connected, right? Because otherwise their gate potential is just floating.
M6 and M12. Where
Yeah.
is
You have
M6
connected
and M12 connected?
no, sorry, not 6. That's 5, right?
M5.
I missed it. Yeah. So you connected M5 and M12. So either of M5 or M12 must be diode connected, right? Or their
No,
gate.
both are biased using an IREF.
Okay, sir.
Is that clear?
Yes, sir.
I told you that it is a VB. VB has to be generated using an IREF.
Yes, sir.
So now the same thing IB by 2 flowing here, IB by 2 in this two, and this is going to get, if this is also biased in a similar way manner so that it is creating IB by 2, and here also is having IB by 2. Therefore, if the W by Ls are matched, this will also have same VGS. This will have same VGS as M9 because I'm putting the same I bias by 2 and same dimensions. So VGS of 9 will be same as VGS of IB M, what do I call it? 14, M15, M16, M17. M17 and M9 will be equivalent, and as a result, the VGS will be similar. Now, therefore, this gate voltage that is developed, I can put it to M10. So this will bias the output stage. And then here you have the high impedance node. You can operate it as a high gain amplifier, which is basically self-compensated. So this is another way of improving overall gain in this topology and getting GMRO whole square gain. So this case, as I told you, why do I like this topology more? Because the compensation is slightly easier. Upper topology, what happens here is that at higher frequencies, you also get a zero path. Zero path means, from the whatever CC you are putting in the compensation, this particular scheme, if you have a, what am I doing? I have to go further up. This CC that you have put at a higher frequency, what it does from this point to this point, it will have a forward path also. Because at higher frequency, 1 upon omega CC is reducing. So this will have a forward path and this will have positive phase, right? Because it is directly coupled from this point to this point. Whereas to this point, it will have a negative phase. So from this point, whatever it comes to the output, it is inverted by 180 degrees because there is a common source path. This path is positive, this path is negative. As a result, these two try to cancel out each other, and that leads to a zero frequency. That zero frequency leads to instability. So again, further there are processes to mitigate that, but that is very sensitive to process variations, etc. So I will not cover that whole thing. I can refer you to some chapter where this derivation is given. You read it up, and then I think in one of my lectures also you will find it more detailed. Have you found any lecture in which I have given this?
Sir, I think there was one lecture. You mentioned adding that resistance, right? The Miller resistor in one of the lectures.
Not Miller resistance. There will be a series resistance over here, R is zero. So
with R
basically, yes. So you need to cancel out that zero. So that is there in one of the lectures. If you have seen the recommended lectures, so you will find it. So again, and that cancellation is also a little problematic. You will not get exact cancellation, and that zero creates some problem. Therefore, if you want to get to more detail, you must make sure that you have seen that earlier lecture. So this amplifier that does not have that zero problem, you don't have a Miller compensation capacitor. If at all you need compensation, you just put additional cap at the output node because that is the only dominant pole. Is it clear? Any question regarding this second scheme? There are better ways of biasing. The biasings that I have shown you here is not the best. There are ways in which you can improve this. Have you studied reduced swing cascode mirror? Reduced swing cascode. I think that I will cover tomorrow. Today we had enough. Otherwise, you will also become saturated. So, any questions before we conclude? I'll give you some assignment on this so that before tomorrow's session you can try to simulate some things. Any question before we conclude? How many people understood? Already some people have ran away. So people have less patience. How many people understood? Other people did not understand. These three people are, already gone. So some people run away. I mean, while the class is going on. Who is this? Afwaban Bernard Mukherjee. Yesterday also I called his name. He was not responding. Afwaban Mukherjee.
I was not there yesterday, sir.
Sorry, I was.
Sir, I was not there yesterday.
So why did you come online?
Sir, I did not understand everything. I will have to watch it another time. See, I think.
Okay. So what is not clear? Which part is not clear?
So some way like trivial parts, but I think I will get it if I watch it again.
No, every time I keep asking what is not clear, every step, every circuit that I'm drawing, every step I keep asking. If you have doubt, you ask. If you don't ask and keep accumulating the doubt, then and you don't go through the video lecture that I have recommended from previous recordings. If you don't do these two things, then I can't help. Have you gone through the video lecture that I have recommended?
Yes, sir, I did so.
Then what is not clear? You can tell me any stage, which stage, what is not clear. Some things I have, as I told you, this compensation capacitor thing also I have mentioned in earlier example, earlier lectures. If you have gone through that, you may find this. Likewise, this Miller compensation, pole zero, all these things should be what is not clear. You tell me explicitly. Yes.
So I
Can you
keep
help me understand?
like forgetting the. Sir, I keep like forgetting the expressions and all.
Which stage? So which part?
The expressions for R out, for example.
Are out. So I have told you people many times that these things, these two things should be, very clear. Looking into the drain, looking into the source, what is the impedance? This case that I have drawn here, and this case, looking into the drain if you have a source impedance connected, and looking into the source if they have a drain impedance connected. These two should be, memorized because these are used in the circuits everywhere. Anything else apart from that? Yes,
No,
anything
sir,
else
not yet.
about? Yes. Okay, so if you don't have any other question, let us stop